Hey guys, hello everyone and welcome to the channel. So as we have discussed on the community tab last day that which topic you guys want. So most of you told me to make a video on F block elements. Now this particular topic is this contains a lot of text, a lot of information is there in that and less of explanation is needed. So I have made a whole lot of slides over there. So I'll be telling you all the important things from this F block element. It will be like a revision kind of video. It won't be containing each and everything from the F block elements, but yet it will contain the most important things which you need and with the help of which you will be able to solve questions in the exam. Okay, so that is something which you are going to get in this particular video. Right now, before starting this video, before going into that, let me tell you that I teach on Unacademy platform and the courses are running over there on Unacademy Plus regarding the revision of CSIR net exams. If you are interested in that, you can join Unacademy and you can take the subscription of that. Do visit my profile on Unacademy. There are videos on F block elements where I have explained whole concept and also discussed about the questions over there. The link for my profile of Unacademy is there in the description of this video, so do check that out. Right now, coming back to the video, so here I am going to just talk about lanthanides and actinides. What are the important terms in this, what are the things which you need to know, and at the end of this video I'll tell you some of the important terms which are there associated with this particular F block element whose definition and whose explanation is needed. Okay, so that's how this video will be done. So let's straight away get into the video. Alright, so the first thing which we are going to talk about lanthanides and actinides is their common properties, like their introduction kind of thing. That's what we are going to do. So first of all, these lanthanides are called your first inner transition series or the third transition series. That's what you can call them, and they come immediately after lanthanum, which is a D block element. Right now they are classified as F block elements along with the actinides. They are commonly known as rare earth metals. So that's what is the name of them. That's what the name given to them is, rare earth metals. Now they are characterized by filling up of 4f energy levels, which we all know, and which are not involved in bonding. Okay, so understand this, that these 4f orbitals are not involved in bonding. All right, the next point is that 15 elements from lanthanum to lutetium, these are called as your lanthanoids according to the IUPAC naming or IUPAC naming, whereas the 14 elements starting from your cerium to lutetium without lanthanum, these are called as lanthanides. So understand the difference. Okay, lanthanoids and lanthanides. Whenever it is asked about lanthanoids, you have to consider this lanthanum, and when it is asked about lanthanides, you have to exclude lanthanum, you have to start from cerium. Right, so that's what it is. That's according to the IUPAC naming. Now these are highly electropositive elements and they have common oxidation state of +3, and they generally resemble each other in their chemical and physical properties. So the chemical and physical properties of all these lanthanides and actinides are quite similar to each other. The generic symbol which is given to them is Ln. So whenever Ln is written, that means it is specified about all the, or it is just a general symbol given for all the lanthanides. Okay, so if a certain property will be associated with all the lanthanides, it will be expressed in the form of Ln. The lanthanides exhibit a number of chemical properties that differentiate them from the D block elements that we will get to know in the further slides. The reactivity of the elements is greater than that of the transition metal and is comparable to that of group 2 metal. So you should know this thing, that these F block elements have similar or comparable properties to that of group 2 metals also, and they are quite more reactive than your transition metals. Okay, let's talk about their occurrence and ore, that in what are the ores and all. So the major source of lanthanides are your monazite sand, and basically they are composed of your phosphates of thorium, cerium, neodymium and lanthanum. Right, the phosphate portion of monazite contains small traces of the other lanthanide ion as well, but that's not of the more importance. The more importance is that monazite sand is actually phosphate of thorium, cerium, neodymium and lanthanum. The only lanthanide that does not occur naturally is promethium. Now this is a very important point. Just mark this thing, that the lanthanide which does not occur naturally is your promethium, and this is made artificially by the nuclear reactions. Okay, so this is a very important point regarding your lanthanides. Bastnasite, which is found in USA and Madagascar, is a mixed fluorocarbonate in which metal is in +3 oxidation state, CO3F, where M is your lanthanum or the lanthanide metal. Remember, we are not talking about lanthanoid, it's a lanthanide over here, right? That means we are excluding the lanthanum over here. Here it should be Ln, okay, that's a misprint, it should be Ln, okay, so you can just write down Ln over here. It provides 20% of the total supply of the lanthanide. So this particular ore, bastnasite, is it is also one of the biggest ore for your lanthanides. Okay, this is about the basics of it. Now let's talk about the abundance and the number of isotopes which they have. So these are the different lanthanides which you can see right now on your screen, and these are their abundances, like the different abundance of them in the earth crust, their relative abundance, and their naturally occurring isotope. At the end of this video, I'll give you a more like detailed tables which will show you a lot more information than these. Okay, so for now, just hold on with me. Alright, so the next important thing about lanthanide is their color and spectra. So lanthanides basically are weakly colored. Same goes for your actinides also, they are also weakly colored. Okay, so lanthanides and actinides both. Okay, the spectra of their complex show much narrower and more distinct absorption band, which is associated with weak FF transition. So these properties are associated with all lanthanides and actinides both. Okay, so their spectra has narrower and distinct absorption band, whereas DD transitions are broad and they are not that distinct. Okay, and they are associated with FF transition. Okay, the 4f orbitals, which are deeply buried or embedded inside the atom and well shielded by 5s and 5p electrons, the f electron are practically unaffected by the complex formation. Hence, the color remains almost constant for a particular ion regardless of the ligand. So you need to remember this point, that the color of the complex of your F block element, whether it is lanthanide or actinide, in both the cases, it does not changes with the ligand. It does not depend upon the ligand environment. It only depends upon the FF transition or the energy difference between the F levels. So the color of the ion, color of the complex, all of them remain quite same, because it does not like the ligand does not affect the color of the complex. All right, so this is a very important point. You have to make this sure that you remember this. The next thing says that the band due to FF transition are sharp, okay, compared to the broad band of DD transition. Okay, so you need to see this point, that the FF transitions which is happening in the F block elements are sharp, whereas DD transitions give you broad bands. Absorption band due to 4F and 5D transitions are also broad and are affected by the ligand environment. So wherever this D transitions come, wherever this D orbitals will come, then the transition will be affected by the ligand environment, unless and until you have F orbitals only, like your FF transition. So whether you have 5F 5F transition or you have 4F 4F transition, in both the cases they are not going to get affected by the ligand environment, and they are going to be sharp. Okay, so these are certain points which you can write down, that FF transitions are sharp, and they are you can say that they are not affected or unaffected by ligand environment. Okay, so that these are two very important points regarding your FF transitions happening in your lanthanides or actinides. All right, let's take the next point then. So this slide shows you the different colors of the different lanthanide ions over here. So these are the different tri-positive lanthanide ion. Their colors are given to you over here, and you can just memorize this particular table. You can see one pattern which you can see over here is that F0, F14 and F7, all three of them are actually colorless. Okay, all of them are colorless. So you have to see like that. The second important thing which you can look upon this table is that F1 and F13 have similar colors. Then F2 and F12 has again similar colors. F3 and F11 has similar color. So what you can say, you can see it is happening in all these things, right? In all like within all the tables. So what you can say, that Fn and F14 minus N, okay, both of them have similar colors, both of them resemble same in color if the electronic configuration is like that. And the next important thing is that their oxidation number should have been same. If you change the oxidation state over here, you can see that your so if you change the oxidation state, the color changes a little bit, like cerium which stays in +4 oxidation state, then samarium which stays in +2 is yellow in color, and so on. Okay, so you just have to memorize these values. Okay, so it is isoelectronic with which and how does the color like varies, you have to memorize. At least you should memorize this particular table, that's more important, the table which is on the left side right now. Okay, the next important point regarding the color and spectra is that all the lanthanide ions, okay, except your lanthanum and lutetium, okay, all of them show luminescence. Okay, so all the lanthanide ion shows luminescence. Europium and terbium show particularly strong emission. Okay, so these are the ones which shows particularly strong emissions, as they are F6 and F8. So they have highest ability to do this particular like emission spectra, to show the emission spectra. That's why the origin of this luminescence is your FF transitions. Okay, the origin of this is your FF transition. The luminescence of lanthanide complex is the reason that they are used as phosphors in the TV screen. We'll talk about that at the later part of this video, where we'll talk about the uses of them and also using the fluorescent lighting. Since 4f electrons, okay, this point is very important. So just note this point out in your notebook, okay, in your short notes or wherever you are writing this, that since the 4f electrons are deeply buried inside the atom, there are no crystal field effects. Okay, there is no crystal field effects which will be there, and since the crystal field effects are very weak, the color of the free ions, aqua ions and the complexes are same. Make this point very clear once again. Okay, so since the 4f electrons are deeply buried inside the atom, there is no crystal field effect. There is no crystal field effect, and since there is no crystal field effect, they are very weak. Okay, like the crystal field effects are very weak. The color of the free ions, aqua ions and the complexes, basically they all are same. Okay, now hence it is not possible to distinguish them between them with the help of color. So color of the complex is not going to help you to find out difference in the geometry, which you can do in case of DD transitions or in the case of transition metals. You know that if you get intense color, probably the complex is of tetrahedral geometry, right? You can do that with the help of your color, but that you cannot do in the case of FF transitions or in the case of F block elements. Let's go to the next thing, that is physical properties of F block elements. So basically all of them are metal and they have silvery white color. They have generally high melting point and boiling point. Both is high, like both melting and boiling points are high, and they are very hard. Okay, this is also important point, that they are very hard. They are very good conductors of heat and electricity. Many of the lanthanide ion form colored ions. Okay, remember this, that the lanthanide ion forms colored ions, but their color is not affected by the ligand field. That also you have to make sure. The lanthanide exhibit a principal oxidation state of +3, in which the metal +3 ion contains an outer shell containing 8 electrons and an underlying layer containing up to 14 4f electrons. Okay, so that's what is given about the lanthanides. So it start from your shell like that your out, like the 4f orbital will have electrons from 4f1 to 4f14. That's what the electronic configuration goes like. Next is that they exhibit paramagnetism because of the presence of unpaired electrons. So they have, almost all of them have unpaired electron, so that's why they show paramagnetism in the like in their physical property. Alright, let's move forward to the chemical properties of lanthanides. Now lanthanides readily tarnish in air and they burn to give oxides. Basically all of them, like all the lanthanide gives you trioxides except your cerium, which gives you dioxide. Okay, so it's an exceptional case, or it's like analogous behavior of cerium, which you can see over here. Now they also combine with the following nonmetals like nitrogen, sulfur, halogens and hydride. So these are also some of the elements which combine with your lanthanide. So lanthanide basically reacts with more electronegative elements. That's what you can summarize from this particular point. It needs more electronegative elements like nitrogen, oxygen, sulfur, halogens or hydride. The hydride are non-stoichiometric but have a composition of MH3. These hydride liberate hydrogen from water. Okay, so that's the chemical reaction which is discussed over here. So if you react this hydride with water, hydride will liberate hydrogen gas. Lanthanide also liberate hydrogen when they are reacted with water, and they form like hydroxides. Okay, so that's what is given to you. A lanthanide reacting with water is going to give you lanthanide hydroxide. Along with that, you will get hydrogen gas, which will be evolved. So that's what is the chemical reaction, which is one of the most important chemical properties of lanthanides. Lanthanide compounds are generally predominantly ionic and usually contain lanthanide metal in +3 oxidation state. As I told you, lanthanide element like they have properties, or they have similarities with the group 2 elements. Group 2 elements form ionic bonds, so they also are quite ionic in nature. Okay, let's talk about those properties of lanthanides which are different from, the properties, so let's talk about those which are with the properties which are different from your D block elements, okay, which are different from your D block elements, or you can say which are different from your transition metals. So the first property says that the wide range of coordination number is seen for lanthanides. They generally form coordination number of 6, 12, but 2, 3 and 4 is also known. But in the case of D block element, general coordination numbers are 4 or 6. Okay, you don't have that much variety of coordination number in case of D block elements. In lanthanide, you have that. Second point says that the coordination geometry are determined by the ligand steric factor rather than the crystal field effects. So ligand steric factors, the steric hindrance between the two ligand, is going to decide that how many coordination number will be there around a particular lanthanide. So how many ligands are going to surround a particular lanthanide is going to be decided by the steric factor of the ligand, not by the crystal field effects, which the crystal field effect which describes the geometry in the D block elements, that is not going to be used over here. The reason is again the same, because the FF transitions or the F block are involved in these, and there is no, they are deeply buried inside, so they do not get affected by the ligand field. That's why. So no crystal field effect, but yes, steric effect is there. Okay, so a bulky ligand will be less, let's say if I have bulky ligands, so they will form less coordination number complex. A smaller ligand or a less bulkier ligand is going to form more coordination complex with the lanthanide. That's what it means. The next thing is that they form labile complexes. Okay, you have to be very careful with these terms. So they form labile complexes and they undergo facile ligand exchange. 4f orbital in the lanthanide plus ion do not participate directly in the bonding, being deeply buried inside and well shielded by the 5s and 5p orbitals. Their spectroscopic and magnetic properties are largely uninfluenced by the ligand. We have discussed this point quite a bit of time, so you might have understood this by now, right? So their spectroscopic properties means their color and spectra, and their magnetic property is also not affected by the ligand. Small crystal field splittings and very sharp electronic spectra is observed in comparison with the D block elements. So in F block element, you see that you have small crystal field splitting. The reason is again same, which we have discussed in the previous point, and they have very sharp electronic spectra, whereas in the D block elements we have high crystal field splitting and broad electronic spectra. So that's the major difference between both of them. The next thing is that they prefer ionic ligand with donor atom rather than high electronegativity. So they react with those donor atom which have high electronegativity, whereas D block elements react with those elements also, those ligands also which do not have high electronegativity, like your carbonyl ligand is there, and these are the ligands which don't have much electronegativity, yet they react with the D block elements. They readily form hydrated complex, we have seen that, okay, and on the account of high hydration energy of lanthanides, and this can cause uncertainty in assigning the coordination number. So the coordination number is basically a part of your steric factor. The insoluble hydroxide precipitate at neutral pH unless complexing agents are present. Understand this thing. You have seen in the previous chemical properties that hydroxides were formed. Now these hydroxides are insoluble and they generally precipitate at the neutral pH unless and until you put some complexing agent. Now these complexing agents have a property to form complex between lanthanide hydroxide and the solvent, and do not allow them to precipitate, and let them stay in the solution. So that's what is the property, or that's what is the use of the complexing agent. The chemistry is largely that of +3 oxidation state for the lanthanides, whereas in the D block elements the chemistry is for the variable oxidation state. You have seen even +7 oxidation state in case of magnesium, to +1 oxidation state in case of titanium and copper. So there are variable oxidation states in the D block elements, but F block elements generally have +3 oxidation states. They do not form double bond with oxygen or triple bond with nitrogen of the type known for many transition metal and certain actinides. So certain actinides also form this triple and double bonds, but lanthanide do not do that. Okay. Unlike the transition metals, they do not form stable carbonyls and have almost no chemistry in the zero oxidation state. So they do not have any chemical reaction or any chemically known substance in the zero oxidation state. So they do not have carbonyls of them, or lanthanide carbonyls are very rarely known, or they are actually not known up till yet. Now let's talk about the analogous behavior of cerium now. So cerium is one of the element which has very analogous behavior. The first of them is that cerium in +4 oxidation state is a good oxidizing agent, as it can be reduced to cerium +3 easily, and it can oxidize water also, but very slowly. Okay. Hence cerium +4 can be used as a good analytical reagent in the aqueous medium. You have seen there are many organic reagents which have cerium in +4 oxidation state. I would like to know from you guys how many, did you guys remember any of the organic reagent or any of the reagent which is having cerium in +4 oxidation state? If you know that, do let me know in the comment sections below. The next thing is that the next point is that europium +2 is a reductant, and it can be oxidized to europium +3, which is a common oxidizing state of the lanthanide. So basically these are the two different oxidation states which we have seen. So generally lanthanides gives you +3 oxidation state. Apart from this +3 oxidation state, there are various other oxidation states also known only for these two elements. Like for cerium we have +4 oxidation state, europium gives you +2 oxidation state. Rest other elements are not known to give variable oxidation state. Okay. So lanthanum +3, cerium +4 with 4F0, and ytterbium +2, lutetium +3 with 4F14 configuration. They are colorless and they are diamagnetic. I told you that most of the elements or most of the lanthanides are paramagnetic except these four. Okay, 1, 2, 3 and 4. These four are diamagnetic and colorless. Lanthanide exhibit +3 oxidation state commonly because first three ionization enthalpies are very small. Both cerium and europium can be separated easily from the rest of the lanthanides due to their different chemical behavior. Okay, for example, cerium +3 can be easily oxidized to cerium +4, which is less basic than the other lanthanide ion, and that's why it can be hydrolyzed easily and it can be separated out. Okay, so hence cerium +3 is oxidized by KMnO4 or bleaching powder to cerium +4, which can be precipitated as a basic salt or as a hydroxide. So from the rest of the mixture of the lanthanide ion, you can easily separate out your cerium +4. In the same way, it's easy to separate out europium +2 because their oxidation states are different. Rest of them which are having in +3 oxidation state, they can be separated by a method called as ion exchange method. Okay, ion exchange method. All right, let's talk about the next point, which says that the ytterbium oxide sulfide activated with europium is used as a red phosphor in the color CRTs. So what's a phosphor? Phosphor basically is a substance that exhibit a phenomena of phosphorescence. So when the light falls on this phosphor, it shines. Okay, it gives you a certain color out of that. Let's talk about the magnetic properties now. So the 4F electrons are responsible for the strong magnetism which is exhibited by the metals and the compound of the lanthanides, which we know. In the incomplete 4F subshell, the magnetic effect of the different electron do not cancel out each other, and they do not complete as they do in the completed subshell, and this factor gives rise to interesting magnetic behavior of these elements. Okay, so there is a very interesting magnetic behavior which you are going to get to know. So at higher temperature, all the lanthanide except lutetium are paramagnetic. So all the lanthanide except lutetium is paramagnetic at higher temperature. Okay, so make this thing very careful, note it down somewhere. Okay, and this paramagnetism frequently shows a strong anisotropy. Now, the next thing is that as the temperature is lowered, many of the metal exhibit a point below which they become antiferromagnetism, that is magnetic moment of the ion are aligned but some are opposed to the other. So, you know what antiferromagnetism means. And as the temperature is lowered still further, many of them go through a series of spin rearrangement which may or may not be in conformity with the regular crystal lattice. Finally, at the still lower temperature, a number of elements become ferromagnetic, and some of the metal have saturation moments greater than the iron, cobalt or nickel. So, that is what it is. At high temperature, they are paramagnetic. You lower down temperature, they become antiferro. If you lower down the temperature more, they become ferromagnetic. They also show strong anisotropy in their magnetic behavior depending upon the crystal direction. Okay, so that is also one of the property, that they exhibit different like value of the magnetic moment if calculated or if that is measured along the different directions. Paramagnetism is one of the magnetic properties having spin orbital contribution. Basically, okay, this point you need to remember that they have spin orbital contribution. Magnetic moment of lanthanide ions are generally well described from the from the coupling of spin and orbital angular momenta, that is called as your Russell-Saunders coupling. Okay, Russell-Saunders coupling scheme, and spin orbital coupling constant are typically large in this case, that is around 1000 centimeter inverse. So in this way, what happens, what are the consequences of these things? Because of high spin orbital coupling, what happens, that only the ground J state is populated. Okay, the ground J state remains populated. You know the J states, right? So the ground state remains. You have studied this in quantum mechanics, and you have studied in molecular spectroscopy regarding the J max level and all. So that's what it is mentioned over here, that the ground state remains populated. Spin orbital coupling is quite large than the ligand field splitting, and that's why magnetism is essentially independent of the environment. These are the three factors which describes the exceptional behavior of the magnetism of these lanthanide elements. Okay, so that's why their magnetism or their magnetic moment is not calculated by spin only magnetic moment, or the formula which we were using for the D block elements. Those formula are not enough to show or to calculate the magnetic moment of these F block elements. You need certain different formula for that. So magnetic moment of these J states are expressed in the form of Landé's formula, and I'll show you what that formula is actually. So the formula is given by this. It's given by mu is equals to G under root J plus 1, and where your G is given by 3 by 2 plus S plus 1 minus L plus 1 divided by 2 J plus 1. You know what S, what L and J are, right? Alright, so let's talk about certain terms which are associated with your F block elements, and one of them is your lanthanide contraction. Now, you know that what lanthanide contraction actually is. It's kind of a revision for that, right? So what happens, that the atomic size of the ionic radii of the tripositive lanthanide ions, they decreases with they decreases steadily from lanthanum to lutetium. So when you move from lanthanum to lutetium, the size or the atomic size or the ionic radii basically decreases of all the tripositive lanthanum ions, lanthanide ions. So that's because of the increase in the nuclear charge, and the electron, because the electron enters in the inner n-2 f orbital, that's why the nuclear charge increases, and because of that there is a decrease in the ionic radii. Now this gradual decrease in the size with the increase in the atomic number is called as your lanthanide contraction. Okay, so that's what is lanthanide contraction. Now it happens in lanthanides, or it happens in lanthanide and actinides both. Basically it's called as lanthanide contraction, but similar effect is seen in actinides as well. So although it is called so, but its effect or the application of that is observed in the D block elements, and that's why the size of the lanthanum and the hafnium is not that different. Okay, they have quite similar sizes, although there are 14 elements between them. So these are certain very basic things which you need to know. Apart from lanthanide contraction, one more concept actually which you should study and which you should read is your ion exchange method. Okay, I didn't included it in this particular video because it will make the video too long. I didn't want it because it's a complete different method, and you will find a lot of text regarding this, and I would recommend you to read it from books, okay, which like you don't have to remember the complete step, you just have to know the certain points that which element will come first during the ion exchange method. So I'll just give you that the ion exchange method, during the ion exchange method, the separation, okay, the separation of smallest ion takes place first, okay, takes place first. So who will come out of the ion exchange column if I have? So the order goes like this: lutetium plus 3 will come out first, okay, then your ytterbium plus 3 and so on, okay. So based upon the size, this will come first and then this ytterbium and all, and that's because the lutetium is smallest in size among all the lanthanides, right? So this is the one of the point which you need to know. If you want to study ion exchange method, you can completely study that, but at least this is something which you should know about that. The next thing which I will give you is certain tables regarding the different lanthanums over here, which are given to different lanthanides, which are given to you, their abundance, and then their isotopes, their electronic configurations, and their color. So we have already discussed about all of them, but yet it's all in a particular single slide, so you can take a screenshot, or if you want you can memorize it. So what you need to focus on is that this promethium does not have any isotope, and its percentage abundance is also 0, because I told you it is not found on the earth crust, right? And it does not have any color as well. So you need to remember that. Rest of them you have to just you just have to memorize them, right? Apart from them, there is one more table regarding your actinides. Now all the actinides are given over here, their symbols are given to you. These are the different electronic configurations of this +3 ion. Actinium are denoted just like lanthanums are denoted by Ln, actinides are denoted by An. Now remember, I have not discussed much about actinides because most of the properties are similar for both of them. The only differences are mentioned over here. You can see these are the, like, instead of 4f there will be 5f elements. Their metallic radii, you can see that the metallic radii is decreasing, and basically these are metallic radii. So ionic radii basically is decreasing because of the lanthanide contraction, which you will see here as well. These are the different reduction potential of them, and these are the different colors of them. The one which are given dash, that means they do not exist, they have been prepared like by artificial means, so that's why they do not have any color. They are produced by the nuclear reactions. So these are certain things which are there. Apart from them, what you have to do is you have to study the theory of your, like, some of the properties of your uranium chemistry, okay. Uranium chemistry is something which you have to study. Now remember, uranium chemistry will also get linked with your nuclear chemistry, so you have to cover all of them, and rest of the thing is completed in this particular video. It's a kind of revision one which would have helped you to revise all the concepts at a particular place. Alright guys, that's all for this particular video. I hope that whatever I have given you in this video, whatever text or whatever topic or whatever notes I have shared with you regarding the F block elements was helpful to you. You guys have got to know quite a few new things, and if you like this video, please let me know in the comment sections below. And I would like to share the PDF of these slides as well, so if you want, so the PDF of this particular content is available in the description of this video, so do check that out as well. And that's all from my side guys. Thank you so much for watching. If you're new to this channel, do subscribe to the channel. If you like this video, give it a like and share it with your friends. So thank you so much for watching and have a great day. Bye bye.